This is a video from section 3.9 in a Calculus 1 class. It's on related rates. Let's take a look at example 1. Each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 square centimeters? So we need to identify our variables. Let x equal the length of the side of a square. That's in centimeters. Let a equal the area of the square. So notice we have a square of side length x. So what's the formula for the area of a square of side length x? Well, it says a equals x squared. Now, each side is increasing at a rate of 6 centimeters per second. So notice I underlined that, increasing. And then it's rate of 6 centimeters per second. That's key. So we just happen to know that dx dt is 6 centimeters per second. We want to know dA dt when a equals 16 square centimeters. So we start with a, which is equal to x squared. Differentiate both sides with respect to t. So dA dt is equal to 2x dx dt. Chain rule. That's just chain rule. But we know that dx dt is 6 centimeters per second. So I need to pop that in. So dA dt is equal to 2x times 6. And so 6 times 2 is 12. And so that says dA dt is equal to 12x. But we don't know what x is. Once we know what x is, we can find dA dt. So we go back to the original equation of a equals x squared. But we know the area of the square in question is 16. So 16 equals x squared. Solving for x, we get x equal 4. And so now I'm ready. I can plug 4 in for x, and I get dA dt is equal to 12 times 4, which is 48 square centimeters per second. And so if I want to make a conclusion here, it says the area of a square is increasing at a rate of 48 square centimeters per second. And that's example 1. So if we take a look at example 2, a cylindrical tank with radius 5 meters is being filled with water at a rate of 3 cubic meters per minute. So we want to think dV dt. Cubic meters, that's those are units for volume. And then minute, that's a unit of time. So that's why, and then let me back up one step. When I look at rate, right, that's a rate of change, and we want to be thinking derivative. So it says, how fast is the height of the water increasing? The radius is fixed. That's 5 meters. I'm going to let h equal the height of the tank. And we're going to let v equal the volume. So the volume is the area of the base times the height. So it's pi times 5 squared times h. So v is 25 pi h. Differentiate both sides with respect to t. So, well, here we get dV dt is 25 pi dH dt. So that's what I did over here. I differentiated this equation with respect to t. And that's where this came from. But we know that dV dt is 3 cubic meters per minute. And we want to find dH dt. So we plug it in. So we say 3 equals 25 pi dH dt. So dH dt is equal to 3 over 25 pi. And so what that tells me is that the height is increasing at a rate of 3/25 pi meters per minute. And that's how we do the second example. And that's a good stopping point for this video. So this is a video on section 3.9 where we did 2 examples of related rates. Thank you.